Dhruvi.
Good evening, everyone. I, Dhruvi Singh, Secretary IEEE, warmly welcome you all to the fourth day of this faculty development program on electric vehicle powertrain simulation using MATLAB and real-time simulator. I would like to extend a heartfelt welcome to Professor Sanjeev Kumar Sir, Coordinator HRD Cell and Convener FDP, Dr. Rakesh Maurya Sir, our expert for today, and all the distinguished faculty members present here today. We shall now proceed to today's highly significant session on integrated onboard electric vehicles, battery chargers with multifunctional features. This session promises to provide valuable practical insights into the modeling and analysis of electric vehicle charging systems, an area of growing importance in the modern energy systems. It gives me immense pleasure to introduce our esteemed speaker for this session, Dr. Rakesh Maurya Sir. Dr. Rakesh Maurya Sir received his BTech in Electrical Engineering from Kamla Nehru Institute of Technology, Sultanpur, and his MTech in Power Electronics and Electric Drives, and PhD in Electrical Engineering from IIT Roorkee. He is currently a professor in the Department of Electrical Engineering at Sardar Vallabhbhai National Institute of Technology, Surat. Over the past decade, he has published 80 plus SCI index papers in reputed journals, including IEEE Transactions, IET UK, Elsevier, and Taylor and Francis, along with numerous conference papers. He has executed sponsored projects on custom power devices for mitigating power quality issues in distribution systems and control of power electronic converters for electric vehicle battery charging. His research interests include switching power converters, high power factor AC-DC converters, hybrid output converters, power quality improvement converters for battery charging, advanced electric drives, and real-time simulator-based control of power converters. He is also a senior member of IEEE and a lifelong member of the System Society of India. With this, I request Dr. Rakesh Maurya Sir to kindly take over this session.
Thank you. Thank you. I hope I am audible to all.
Maurya sir, you are very much audible. A small request, just drop your screen, that Google Meet screen, little bit down. It is on the PPT.
This one?
Yes. Actually, some picture-in-picture mode is on. That is why it is come up.
That need to be minimized, na?
Yeah. Yes. Now it's fine. Now it's fine, sir.
Okay. So, good afternoon, everybody. First of all, I thank you, administration of HBTU. I think administration and coordinator of this short-term program for inviting me as a speaker for this audience. I hope one doubt I would like to clarify whether we have students of undergraduate.
No, sir. All are. This is the faculty development program. All are faculty, and very few, 2 to 4, are research scholar.
Okay.
So all are faculty development program. We have received 242 application, but those who are the student, we have already eliminated. So all are faculty.
So thank you. So now I am going to interact with the faculty. They are the highly rated person of the society. They are going to train the future of tomorrow in terms of the technical education. Okay. So this is a small setup which we have started since July 2014, just after graduation, our research completion. So as I say, it is known that the research is the ongoing process, and PhD is just start of the research. It's a training for the research of the tomorrow. So in 2014, I just completed my PhD and then I started my lab at our place. And over a period of time, we make a team of around more than 13 research scholars, those who have completed, and 3 are ongoing. Apart from this, we have a very good pillar of our MTech student, followed by the BTech students. And of course, to do the research, we required funding. And funding, we are supported by the Department of Science Technology, then Gujarat Council of Science and Technology, then CSIR, and of course SPN. The key research area where I used to work is mainly control algorithm for power filters, power converters for EV charging, and very recently I am working with the multi-input, multi-output power converters for microgrid and nanogrid applications. And at the last, the multi-phase induction motor drive and its application. So this is the key area where I'm at present I'm working, and this is a small startup which we have initiated, and now it is matured as a company, and it is contributing to the society by providing the assistance in the field of power electronics, setting laboratory, setting making equipment, custom equipments for the industry also. We have a good support of gate drive, our novel gate drive circuit, and they can be operated at more than 150 kilohertz switching frequency. We are also making voltage and current sensor board for research as well as the industry practice person. So now coming to today's discussions, my presentation is like it's a very small introduction followed by the simple research highlight which we have done at our laboratory. So mainly I'll be focused on the integrated onboard charger and some of the future directions, future practice which we are expecting the person, those who are involved in this area, that will be helpful for them. So now coming to the first question, why electric vehicle? I think it is open, and there are various debate has been conducted at various places, and it is well known that electric vehicle, why electric vehicle, the future transport. Can anybody tell? Anyone from the audience? Anyone? Because many times when I ask this question to audience, they used to say it is pollution free, it's like that. But are you is the electric vehicle is the pollution free means of transportation?
It is expected from the participant. They actively participate. The energy
Because
which
that will help us to make our session live, because after lunch and especially after 4 p.m. onward, it's very difficult to inculcate the information. Okay. So the mic, as I said, if you are agree with the pollution-free environment, of course, it's a very debatable talk. The reason, suppose the electric vehicle battery which you are charging from our power grid. Suppose in India we have a millions of vehicle running on the road, and if they are taking power from the conventional power grid, again you are consuming electricity which are coming from any thermal power plant or any source which is creating pollution in the environment. So this is an additional burden to the society, where you are replacing the conventional vehicle which is running on the urban area, for example, but they are polluting environment of the power station where the electricity is generated. It is the additional burden given to it. So the pollution free environment you can claim at the urban, while the use of electricity in the urban area mostly. but indirectly they are polluting the place where the electricity is generated to charge the electric vehicle. So if you are able to charge the electric vehicle through the green source of energy like solar, uh, hydro, etc., then you can claim this is a sustainable or this is a pollution-free environment, even at the place where the electricity is, where the electric vehicle is being used, and parallelly where the source is used to charge the electricity. But if you are charging electric vehicle through your power grid, and you are taking power from the conventional source of energy like thermal power plant and other such plants, so probably this is not a claim that it is a pollution free. Okay, but other added advantage is about the technology. Like electric vehicle is a highly, all the electric machines which are used for driving electric vehicle, they are highly efficient than its counterpart like petrol engine based vehicle, like IC engine based vehicle, because the efficiency of any mechanical system, IC engine as well as their transmission system, they are roughly around 17 to 21%. Whereas electric vehicle, whether you claim for the motor or for the converter, for any sort of conversion, it's roughly 90 to 95% efficient. And if you are designing electric vehicle with a transmission, gearless transmission of power from the motor or from the battery to wheel, probably it is significantly increased as compared to its counterpart, petrol engine or IC engine based vehicle. So what I want to tell here, technology wise, electric vehicle is much mature than the means much efficient as compared to other vehicle, means IC engine based vehicle. At the same time, if you see the battery technology cost of the battery is going down, and that will give us the boost to reduction of the electric vehicle cost, because this is the cost over at this is the battery cost towards the battery, and after 5 years it's research in the reuse of the battery, dismantle the battery, and at the same time uh, uh, disposal dispose of the battery is a challenging task. So those who wish to do a setup, either company or planning to set up the business towards the battery, they can think of, if they are having, let's say, these are the era where we are using, yeah, this is the last 2 3 years we are using electric vehicle in mass, whether it is a two-wheeler, three-wheeler, or four-wheeler. But after 5 years, these batteries are going to become a problem for the society. Their disposable is going to become a problem for the society. So how to use the reuse of the existing battery, which is coming as a dump for the other from the EVs, that you need to think of. So we need to train the students so that they can think the 5 year, 10 year ahead of a problem of 5 year, 10 years, or coming problem of the society, so they can address that problem. So that is more important from the future transport point of view. Now, here the pollution, as I said, the of course the urban area where the large number of EVs, large number of three-wheelers or two-wheelers are being used, of course the pollution will be improved. Means air quality will be improved by use of the EVs. But in total, if you talk about the pollution, if you are using from the IC, means conventional source of energy, like our thermal power plant and other source, they are this is not the appropriate way. So you need to develop a sustainable source or green source where you can derive energy from the solar or hydro, and that is being used to charge your electric vehicle battery. Okay. Now we have variety of option, of course, from two-wheeler to four-wheeler, and even the Airbus, these buses, we are having variety of segment of electric vehicle available. So Now coming to the challenges of electric vehicle in India, as I said, we have a still lack of the clean energy available throughout the places. Most of the energy which we are receiving through our near to our place is coming from the power grid, and there we are. It is mainly contributed by our uh, uh, conventional energy sources. So we need to enrich our electric sources through the green energy. We should facilitate the solar power generation, hydropower generation, the localized generation where the clean energy is possible. The second challenge is the charging infrastructure. We don't have adequate charging infrastructure in the society. Still, we have, if you see the existing system, let's say the two-wheeler or three-wheeler, normally the three-wheeler is very popular. E-three-wheeler is very popular for the passenger transport. You might have heard the e-rickshaw. It is being used even in the rural area widely. So, but the charging infrastructure available at the society is very less. They are using their home socket at their village, at their home, to charge the vehicle. So we need to strengthen our existing infrastructure to charge, to make a setup, and then we can felicitate more about the electric vehicle. Now, third is the suboptimal battery technology. So if you see the growth of the battery technology, we have a lead acid based battery. They have a very poor charge density along with the bulky size. And again, you require to fill the liquids or electrolytes oftenly. So we need to think of the, you have to cope up with that battery technology, and after the certain years, like 5 years, you have to see the of the EVs. Then what is the secondary use of the EV? Then how to segregate, how to create, dispose of the e-waste, or is it possible to again make the same, recover the same battery? So that all associated research is required, and we need to train our student to do the think about this technology. And the last is the human tendency, persistent resistance to change. We are having a, even Indian mentality is, we are having a technology and it is used presently, and we expect that technology should persist for a longer duration. Means even for entire life, I will comfortable with my IC engine, our petrol vehicle. But because we are not ready to accept the new technology quite often, so we need to think of this also need to be think. If the technology is going to change, you have to adopt, you have to train the people in such, you have to educate the people so that they can ready to adopt the change in the system. Okay. Now coming to EV, electric vehicle in general, there are 6 segments where the power, where the research can be done. One is the charging infrastructure, that is very important for us. So this is the charging infrastructure. So based on the power level, the chargers are classified as the level 1, level 2, and level 3 chargers. Normally the level 1, level 2 chargers are, they are located, they are very slow charger. Like level 1 is a separate charger, it is a slow charger. Level 2, this is rated up to 2 kilowatt, level 1. And level 2 is up to 20 or 22 kilowatt. They are also placed inside the vehicle. And level 3 is the fast charger, which is more than the 20 kilowatt, and it is normally called as the DC fast charger. So if you want to make your commercial business, you need to start with the level 3 chargers. Okay. But as far as the level 1 and level 2 is concerned, most of the manufacturer, they provide onboard charger, and they are inbuilt in they are located inside the vehicle itself. So again, for the location, if your charging stations, they are located off the board, it is so it is called the off-board charger. And if the charging facility is available within the vehicle, and you have a converter inverter inside the vehicle, then it is an onboard charger. Now, some of the technology now coming up with the integrated onboard charger. So here I will be talking more about the integrated onboard charger, where we do not require any infrastructure for that. We do not require any separate component for the charging. Existing converter can be used to charge the battery of the EVs. Now, second is the battery technology. As I said, the lead acid battery is a very old and conventional way battery setup, but there are a lot of improvement in terms of the energy density, in terms of the life, in terms of the quick charge. So the fuel cell as well as the lithium ion battery are also common. So the lithium ion battery nowadays is a very common practice used in the EV setup. And but here we can think of, even can we integrate lithium ion battery along with the ultra capacitor or fuel cells that can be work together, but like whenever you require fast acceleration or deceleration, can we use the fuel ultra capacitor along with the battery to cope up the requirement of the current? And the later on, when the machine is when the vehicle is running on the road at a very steady speed, then the lithium ion battery can provide the support. So whenever during the fast charging or fast acceleration and deceleration, we can take energy from the other source. So nowadays the only either lead acid in three wheelers is like auto rickshaw and etc. It's available. Whereas can we use the lithium ion battery like in the good car, good electric vehicle? The lithium ion is a very common. But can we integrate the lithium ion along with the ultra capacitor or the fuel cell to provide the energy at that whenever it is required during certain operating condition? So this can be done at the battery side. As far as the motor technology and converter is concerned, as you all know, the EV is having battery, and battery output is the DC power. It provides the DC voltage, means power in form of DC. But the motor which is used to drive the wheel, they are either PMSM, permanent magnet synchronous motor, or induction motor. Now we have a switched reluctance motors are also going to popular. Then DC motor that can also be used. So among the available machine, how these all mostly required the AC supply. So we required an inverter to convert DC into AC. So that infrastructure is also required. So we have a very well proven voltage source converter, particularly PWM rectifier or DC to DC converter to make the power flow from the battery to machine through this power electronics converter. So these two components are very important, like machine as well as the converter and the battery. Of course, the passive elements like capacitor, inductor, some relay arrangement are very essential in part of the power electronic circuit. So they are also being the part of it. Then microcontroller, you can use the microcontroller that STM32 or other TI based controller so as to control the entire system. Okay. Now coming to the propulsion type, there are various type of vehicle available. Either it is a purely battery operated electric vehicle, it is called BEV. Second is the hybrid electric vehicle. It's a very popular. And as I said, it is with some fuel car-based electric vehicle, or it can be clubbed with the lithium and fuel cell, lithium with ultra capacitor to do the work. So these all are the battery technology they can claim, like BES, HVS, and fuel EVS. So apart from this, whether this electric vehicle is only used for means of transportation, this is the question. Can we use optimum use of electric vehicle? For example, in most of the offices, when you go to the office, let's say I am having electric vehicle, and when I'm coming to office, most of the time my vehicle is parked in the parking area, or at the night when I go back to my home, my vehicle is mostly parked in the vehicle area. So are we using optimum use of our electric vehicle? Of course, no, because during the transmission, during the travel times we are using, and for entire your times, like out of 24 hours, probably 1 hour optimum is the up to 2 hour is the maximum use of electric vehicle for a general people. So can't we use the electric vehicle for the multiple functional reason, multiple functional? For example, can we during the charging we can take power from the grid, but if the vehicle is available in the parking area and your battery is sufficiently charged, can we feed power to grid and take money from that? It is maybe the possible. So that is the vehicle to grid. Sometimes when you are going on the road and your fellow travelers or fellow uh, driver, they are having another car, so can you give power to your other vehicle, v to v transaction? And suppose if you are going to some outing where the some isolated load is required, yeah, suppose you are going in the party and some yeah, suppose you are going to attend somewhere the function, and if the functions required additional load, so can we give power to that particular load, so vehicle to load or vehicle to home? So what I want to tell, electric vehicle have an additional feature as compared to the conventional vehicle. It can be used in varieties of way, like vehicle to grid, vehicle to vehicle, vehicle to home, vehicle to load. So this is the optimum use you can use for the machine. Now this is the charger classification which I have already done. Now as I said, the onboard charger. So in for a given electric vehicle, you have a battery bank, and there we have a charge onboard charger which is already inbuilt in the by the manufacturer. So whenever you require to charge, you normally for the level 1 charger or level 2 charger, this terminal output means input socket is connected to a convenient place, and it can be used to charge your electric vehicle battery. So now like this, so here we have a provision. You can directly plug in to this battery, lithium ion battery bank can be directly plugging to the fast charging station, like fill station, where if suppose you are going in the market and you want to charge your vehicle on petrol fill station, then you can use the DC fast charger and you can plug in this socket. Whereas this red color socket, here the onboard charger terminals are available, which you can use at your home or at the place where, let's say, the large time you have a large time and you want to plug in through your own charger. So the onboard charger can be utilized for that. So these are the two socket available in most of the electric vehicle. Now coming to the classifications, depending upon the power level, the onboard chargers are classified as a single phase and three phase. And again, you need to have isolation. So we need to isolated, non-isolated, depending upon the type of functionality, like you use G to V, V to V, or V to G, then you need to enrich with your bidirectional charging technology. Sometimes we required the wired charging, which is called the conductive. If you have an inductive charging, for example, you required a wireless flow of power to charge your battery. So this is also available. So there are the variety of technology depending upon the application, depending upon the power level, and uh, so it can be implied. So this is the uh, now let us come to the some of the because when you go for the any design the vehicle battery, then you need to think of what is the market, what is the vehicle available, and what are the rating of the battery pack, are the converter size, motor size, and what type of AC sockets are available worldwide. So if you look at the some of the, just for a literature, if you look at the any of the vehicle model, uh, here the first three, second as well as a vehicle model. So the battery is normally, let's say here we have a 22 kilowatt battery with 72 volt nominal voltage. Similar, this is the range which I would like to tell you. So 22/72 or 22/42, and the next is the this is 72 to 44 are the voltage level. The onboard charger which is available in the vehicle model is of 3.7 kilowatt charger, 3.7 kilowatt charger, and the motor which is used to drive the entire system is of 30 kilowatt, 47 kilowatt, and they are operated, they can be AC plug-in facilities are available. So this is for a few first two model. Likewise, if you go for the few more vehicle, like let's say that I'm talking about the eighth one, that is the Chevrolet Bolt model. It is having a battery capacity of 60 kilowatt with the voltage of 350 volt, and their battery size their charger capacity is 7.2 kilowatt. Okay, but if you see the most of the our onboard charger rating, the more variety, it is 3.7 kilowatt. Most of the model they have a charger capacity of 3.7 kilowatt. So if you, and motor rating, if you want to see, it is over, in some case it is less, but in most of the case it is over 100 kilowatts, like 160, 110, 70. Similarly, some Tesla model, if you want to see 9 to 11 serial number, they are the vehicle of Tesla, and their battery capacities varies 75 to 100 kilowatt with voltage of 370, 350. So this is the a rough idea what type of the battery size are being used in the vehicle. At the same time, onboard charger, we have a onboard charger capacity. They are relatively, at the most, they are 10 kilowatt. Here it is a 3.7, 3.7, but in general, we have a 3.7 kilowatt charger. Capacity is very, very less. So this is the size of the battery used in the electric vehicle, and what is the charger rating which you are being used to charge the vehicle, and available infrastructure like motor capacity, obviously, and the single phase, three phase power supply available. So looking to this rating of the vehicle battery motor capacity, we need to think of how best we can think of how best we can make the integrated chargers. This is the level 1, level 2. I have already said in our previous discussion. So as I said, in coming to the layout of the system, we have a battery pack here, and this is the onboard charging facility. Here is the converter which is located in the board, and that is called the onboard charger. And so when the vehicle is running on the road, then use of onboard charger is probably nil, and then the battery is providing energy to motor through bidirectional converter, DC to DC converter, and the traction drive, which we call it inverter, voltage set inverter, and the motor. So the flow of power is from battery to conventional DC to DC converter, then VSC, and then motor. And the motor is connected to wheel through transmission system, or without transmission. Means it is directly mounted on the, like hub motor. They are directly attached to wheel itself. So the flow of energy is from battery to wheel through the motor, through inverter, DC to DC converter, inverter, and motor, and of course some lighting in the vehicle. So this is required. But whenever the battery is required to be charged, then the onboard charger terminal is a plug-in in the available grid, and it can feed power to charge the battery to this system. So in most of the place, if the charging is not required, then the onboard converters are kept idle. And when you are charging, then the DC to DC converter, inverter, as well as the motor becomes ideal, because when battery is required to be charged, at that time you need to park your vehicle, and you have to establish the charging function. So here, can we optimize, can we think of to utilize the existing vehicle component, those who are part of the propulsion system, those who are part of the system when the vehicle is running on the road. So that can be so so here we need to think of the integration of the charging facility within the vehicle. So to look into here, the concept of integration is done. So this is the schematic diagram of the vehicle. Let's say this is the wheel which is connected with the motor and motor. So during the healthy condition, the battery is providing energy to motor, and motor is used to driving the wheel. So power flow is from the DC to DC converter and VSC. But when the battery pack is drained and it is required to be charged, then you have to plug in not from the separate through the separate onboard charger, but here I can utilize the motor winding, and that can be plugged in through the motor winding, and then the VSC can be operated in bidirectional power flow. Here bidirectional DC to DC converter. So the flow of energy from the to battery is going through the motor converter, DC to DC converter, to charge the battery pack. So if you look at the rating of the motor, which was already I have been discussed, the motor is designed to carry around more than 100 kilowatt power capacity. During the propulsion mode, the VSC convert size is also big. Large size of rating is required. Bidirectional converter is also part of the flow of the energy when the driving system. So these ratings of the rating of the converter, switches, cabling, and motor armature, motor windings, they are designed for a high rating current. So you can charge your battery pack as per the required rating of the battery through this integrated concept. And here there is no limit of like in onboard charger. Here you have a 3.7 kilowatt power capacity. So though you are charging battery pack of, let's say, the 100 kilowatt hour, but you are flowing the current slowly through this converter because of the restriction of the charging rating. So here by integration you can increase the you can charge your battery pack with the larger current, and therefore the charging time can be reduced. So the integrated charger facilitate the power level of even fast charging also. It's the level of level 3 charger also. So that's why this integration is proposed. Now if you look at the power circuit, every electrical vehicle, the power, we have a battery, and this is the inverter which is used to drive any AC motor, let's say the induction motor. So during motor, the power is going to flow from battery to motor through this inverter. But if I want to make the integration process, then let's take the same technology which is already there with the, let's say, the two-wheeler. We have a two-wheeler, so there is a hub motor, or there may be the Tesla vehicle, so we have induction motors, and then there is the induction motor, then VSC, and then battery pack. So only the three components are involved: VSC, battery, and the motor. How we can reconfigure? So suppose, let's take this example figure, left side figure. If here is the R1 is the relay. If you turn on at position 1, then this is the induction motor where the windings are L11, L12, L3. With all the three windings, they may be connected in a star, and the battery switch is connected to one. It means battery is providing energy to induction motor through this inverter VSC, and it is acting as a propulsion mode. Like this way it will start working. But if you switch this position 1, let's say your battery is drained, you want to charge the battery, then you have to switch this relay to position number 2, and here the battery terminal is switched to position number 2. By doing this, you can start the charging through the AC, and if you connect at position number 2, you will find the first two cell winding of the machine, like L11 and L112, they are the inductance of the two phase of the windings. They can be treated as the induct L1. It is a it and the first two leg of the VSC can be used as a single phase inverter, and the last leg, which is connected through the blue color winding, they can be part of the DC to DC converter. So just to incorporate one relay arrangement, two relays, relay 1 for this 3-pole concept, means it is a 3-pole double throw, and here are two relay 2 for one single pole double throw. So by this two arrangement, you can inbuilt this integrated charging in the two-wheeler, and the same can be done for the three-wheeler also. And if you see the technology, this right side figure, it's a very mature. The single phase PWM rectifier acting as a front hint converter. From the single phase supply, it can make the sufficient DC voltage at the DC link, and this the last leg of the VSC can be used, a third leg of the VSC can be used as a bidirectional DC to DC converter, like buck converter, to charge the vehicle. And whenever you flip to position number 1, then the battery provide energy to motor, and motor is driving on the road. So this is so during the propulsion mode, or when the machine is running on the road, like a vehicle is running on the road, it is just at position 1, and whenever the charging is required, you have to shift to the position number 2. So the same component is going to charge your electric vehicle. So this is the for the integration of system. This is how it is operated when you are charging from the grid. So as this circuit is very popular, very well proven, so I will not going to talk this in detail here, but this can be done. This is a small setup which we have done, and we have demonstrated this hardware through the same concept we have implemented through the hardware also. This is the sum of the result. Without PFC we have done it. Then some DC voltage we have taken, and then again through the fluke we have taken the result. And when we incorporated PFC operation, then we have significantly improved the THD. So that is part. Now coming to the second part, let's say the vehicle, we are having four-wheel drive system. Let's say the electric vehicle. This is a schematic diagram. I will come this at later stage. So let's say, let us understand this particular part. We have a battery bank system. We have a battery bank, this black in between, this is a battery bank. They are going to power, here we have a 4 induction motor, M1, IM1, IM2, IM3, IM4. This 4 motor is connected to each wheel through their respective 3-phase voltage source inverter, and the DC link of these 4 is common, and they are connected to battery bank. So there is a one relay. If you connect this relay to K, switch K or the relay, when the switch is connected to P, it is acting as a propulsion mode, means you are powering, battery is going to power individual machine through your individual VSC. And during and when they are required to be charged, battery is required to be charged, then this K switch is shifted to C point, and obviously here, as per the socket, you have to connect to the single phase supply, and then the first set uh, IM1, IM2, and VSC1, VSC2, they are acting as a front end converter, so they can convert AC into DC. And this DC, the rear side converter and machine, they can be made as a 6-phase buck converter, multi-phase buck converter. It is example of multi-phase buck converter. So the rear wheel converter means VSC along with their motor can be utilized as a DC to DC buck converter, and they can use to charge your battery with a very high rate. So here also we can use this component to facilitate charging during the charging situation. Only you need to incorporate one relay switch where the charging can be established. This is the another topology which we have explored. So this is the setup which we have developed in our laboratory. As I said, we have a 4 motor. If I have used this 4 induction motor, they are connected, and obviously there is a VSC located, this VSC1, VSC2 for these 2 motor. Then here we have a VSC3 and VSC4 for next 2 motor, and then inverter convert, then their power electronics circuit, sensor, driver, they are used to do the entire thing. Here is the black portion. We have a battery bank, and they are going to operate this one. But so this is the small setup which we have developed in our laboratory with the integrated concept, just to demonstrate the charging. As far as the control of the front end converter is concerned, it's a very simple, just like a PFC boost converter. I hope everybody know the PFC boost converter. So there is no need to discuss much about that. So it can be used to turn on, when you take power from the grid, you have to maintain the DC link voltage constant. To make the PF unity power factor operational. This concept we have developed at this particular stage. And now this is a structure for the case of the battery. Battery is charged, you have to maintain the either constant current charging or the so you have to take power from the you have to take the through the sensor, you have to take the battery voltage as well as the battery current, and then based C rating, recommended C rating for charging the battery, you have to set the battery, and then this PI controller signal is going to come here. And now the depending upon the state of charge of the battery, or here the role of BMS is important, and that is going to decide whether your battery is to be charged through the CC mode or the CV mode. So this signal is selected here. This can be used as a driver circuit and some logic circuit to trigger our device, our pulses. So this is just automatic control structure for any converter to be charged. Now let us come to the integrated two-wheeler drive car. So suppose you have there are many e-vehicle which is available with the rear wheel driving. So in front wheel you have one, let's say I'm talking about the Tesla model, where induction motor 1 is going to drive the front wheel. Then here is a dedicated voltage source converter for the rear wheel. Also we have a motor, and it is connected through the VSC, and there is a battery bank which provide energy to both front as well as the rear wheel. So whenever this is the relay, whenever this relay is connected to point P, it is going motor, and the entire system is running as a vehicle, and that vehicle is, that method is called that process is called running on the road. So during that position, the battery provides energy to and these motors are working as in coordinated manner on the road. But whenever the driving, your battery is drained and it is going to recharge, then the vehicle is kept rest, and this switch K1 is now connected to point C. So moment you connect to point C, the socket is connected to the single phase supply. Then the front end converter is connected to DC, and then the rear wheel motor and their VSC, they are configured as a DC DC converter, and it is going to charge your battery bank. So as the rating of this kind of converter is very, very high, so they can be allowed to charge your battery automatically. This is the way you can establish charging between integrated charging in two-wheeler electric car. Okay, so the same concept is it is reconfigured as this one. So now here again the same thing. The some topology is changed, because if you see the I have given this four-wheel drive. We can configure, we can use the front wheel converter as a PWM rectifier. So there are variety of PWM rectifier, like three-phase PWM rectifier. So there may be a Vienna rectifier. You might have heard the Vienna rectifier. So can we use this two wheel means six switches which can be configured to make the Vienna rectifier here? So that can also be done, and that we have developed and we have tried to test. So this is the configuration we made, where L11, L12 and L13, they are the part of induction motor winding. And obviously the one VSC, if we are not giving any pulse, so this will act as a diode rectifier. So this is the three-phase diode rectifier. And second VSC, you have to configure it as a Vienna rectifier topology. So the DC link is available here. And the other two set of the VSC and induction motor can be configured as a DC to DC converter. So here the first setup is going to convert AC into DC, and later on DC is going to utilize by the bidirectional converter, DC to DC converter, to charge your battery. So this is the detailed operation we have discussed. You can refer the paper and you can get the detail. So, but the essence of the control is the same. It is a BFC boost converter. So if you want to just use the BFC boost converter, so suppose you want to maintain the DC link constant, so you need to sense the reference voltage boost converter, the reference voltage which you have to set at the DC link, it should be more than the peak of the input voltage. Then only the PFC operation will be maintained by the PWM rectifier. So here the reference should be set more than the peak of the input voltage of the supply, and the actual voltage is sensed and it is passed through the PI controller, and this control voltage is now the output of the PI. This is the unit template generation, because the AC supply you are sensing, and you have to make the unit template and it is to be multiplied with the output of the PI controller to get the current reference. Now this current reference is the sine wave which you are expected your load current, your motor current should follow this sine wave. So each individual winding current is now compared, and it is maybe the pass through the hysteresis controller, or it may be the pass through the PI controller, PI current controller, corresponding pulses. And then it is compared with this carrier wave to generate the pulses for the switches. So this is the general schematic diagram of control circuit, and it is available most of the places. It is available in most of the BFC converter. So it is very generic. This is again a setup for, as I said, for the single machine model. here is the same topology which now let us look at this is the one experimental setup which we have made with the single machine model. This is the induction motor. Single phase supply is now converted into rectifier. This is the VSC, and now this is the small load connected at the DC link. So we have maintained 72 volt at the DC link. This is the STM32 rectifier means controller. Here without PFC we are maintaining this. Now we have switched on the driver circuit so as to start the operation of the inverter. And now see, during the operation, when the entire system is running, your input current THD come down below the 5%. And here the purple color is the motor current, and in this first three is the winding current, motor winding current. So this way we are going to, and see at the DC link we are maintaining 108 volt. So this is the setup which we have developed for the front end charging, for front end converter. Like let me talk again. This is the this is the model which we have a front end converter model. We have demonstrated just now. So again, if you wish, I can read. Okay, so again you can see this is the single machine which may be treated as the front end drive. Then this is the grid is connected. This VSC is used along with the driver circuit. This is the DC link load is connected. 72 volt is the just with diode rectifier and all. And then this is the STM32 F407 microcontroller. And here is the input side power quality demonstration. Moment the driver circuit is on, now the VSC start working, and the input current THD comes down to 5%, below 5%. See the current rating of 4.4 ampere current, and see the waveform, motor current waveform along the supply current waveform. They are almost sinusoidal, and this is the demonstration of experimental. And see here the VSC is now DC link voltage is 110 volt. Okay. So this is about the demonstration, and these are the few test results of the same which we have captured, and we are going to show you. So this is the situation when the VSC harmonics is demonstrated, current ampere, then VSC, all the THD motor winding current as well as the source current. Then during the supply fluctuation also we have captured, and we are trying to see the result. This is the one more aspect we have covered during this is the sensor reduction technique. This SRT is very important when you are going to optimize the cost. Everybody wants our cost of our products should be as minimum as possible. So can we remove the sum of, we can make the sum of the optimization of our component, like we have removed the onboard charger from the board, and we have integrating the facility of charging within the component itself. Here the motor sensor reduction can be possible. So in the actual running condition you required 3 current sensor to sense the motor winding current, and their current control, it is required during the current control of each machine. Can we replace this by a single current? So we can incorporate single current at this particular node, and by knowing this current we can reconstruct our individual motor winding current. So there is a technique, and the paper already available, the published paper is available, and here you can make the optimization of this. So the same concept, same converter, same topology, we can use the sensor reduction technique to improve the cost. Means it's, you can reduce the cost of the system by reduction of the sensor. This is the same thing when the, as I said, when the rear wheel machines are there, can we use this rear wheel motor drive infrastructure as a DC to DC converter? Of course, yes. As I said, the rear wheel we have two motor, IM3 and IM4, and they can be reconfigured make as a DC motor. So here the VDC is coming from the front end converter, and all the other VSC, which is for the rear wheel, they can be utilized to configure as a multi-phase buck converter. I think the multi-phase DC to DC converter is very popular topology, but here you need to operate your each individual leg by interleaved manner. Moment you give interleave control of the machine, you can reduce the ripple in the motor drive, and that battery current here, the battery current will be smooth and it can be used to charge. As the windings are connected, so suppose if each is designed for carry, let's say that 10, it is designed to carry more than 10 ampere current, but let's say during charging, if you are giving 10 ampere average current by each winding, so the total 6 current, they are parallelly going to uh, impress in the DC battery, in the battery. So you are going to get the total 60 ampere current during charging. So if you want, you can make a fast charger. The same infrastructure which is available of machine, they can be utilized to charge at a very high rate of charging. So this is the SRT integration. As I said, in order to same here, we have a to measure current of each motor winding, you can incorporate 3 sensors here, or you can imply this sensor at DC link side. You can imply sensor and you can reconstruct the motor winding current by utilizing the technology. So this is the attempt which we have made. First, we have tried at a different duty ratio what should be the profile of the input current, this current profile, and based on this is the input current profile when they are operating at a different duty ratio. Later on, this flow chart demonstrates in what case what should be the current, and then the same thing we have applied in DC multi-phase DC to DC control, and then we have tried to see. So the same model which we have developed here, again you can see this is the demonstration of a three-phase DC to DC buck converter, interleaved buck converter, interleaved, and here it is a DC link is generated. Now through the same controller NVSC, we are going to charge the battery pack. See here, this is the 4 battery connected, and 110 volt is the total volt DC link, and these are the sensor utilized to sense the current. These motor windings are utilized as a filter inductor to realize the 3-phase DC buck converter, 3-phase interleaved buck converter. So this is a small setup we have developed for the rear wheel charging, which can be used as the DC to DC converter. Obviously, here 3 inductor, when they are added, you can get the output ripple. It's a ripple free, almost negligible ripple. So interleave control of each phase uh, facilitate the control of cancellation of a ripple in the inductor, and therefore the total current flowing in the battery is almost ripple free. Okay, this is the hardware as well as their simulation result which we have shown. Similarly, the each motor binding and their corresponding voltage, it is demonstrated in the hardware in the simulation, as well as their corresponding voltage and current in the simulation. This is during the fluctuation, during the change in current when you are doing. So this way they are trying to maintain the total current and the individual inductor current. This is same waveform, zoomed waveforms they are given. So this is the current, actual current flowing in the sensing through actual current of the inductor, and where we are using the SRTs, sensor reduction technique, we are using the so this is the blue color shows the current waveform which is regenerated after the some calculation. So the average value of current, reconstructed current, is same as the average value of the inductor current. This is again one more waveform after reconstruction. So it validates the concept of sensor reduction technique. Same thing, as I said, you can use 6 winding, means 2 motor of the rear wheel can be make as a multi-phase DC to DC converter. So the first 3 L1, L2, L3 can be considered as a one motor. L4, L5, L6 can be considered as the second motor, and the 3-leg VSC of one motor and other 3-leg VSC of the second motor, they are configured to make the multi-phase 6-phase interleaved buck converter configurations. As there are 6 phase, so to control the machine you require the 6 sensor. Again, it's a bulky, it's a costly affair. So can we utilize one motor by reduction of the applying some sensor reduction technique? So we can remove this all motor machine sensors, and I can imply sensor at the DC link like left side of the figure, and I can sense only the first sensor IDC, and based on that we can make the other winding current, and that can be used to utilize for the control of the machine either through the charging or as a motoring operation like propulsion mode also. So sensor reduction technique can be implied in multi-phase machine. Again, this is the same. If suppose if you are operating duty ratio less than 1.5, so if you are sensing the current DC link is like this, it is same as the motor winding current. So this is, if the duty ratio falls in this category, then you have to manipulate, you have to calculate the some, you have to apply some this formula to get the reconstructed inductor current. So this is the way you can do this. Since the time is less, I am not able to discuss each thing in detail, but you can refer our paper, published paper, and you can get this technique. It's available. Okay. So these are the some results which we have shown. We have validated our sensor reduction technique in a multi-phase, 6-phase DC to DC converter with interleaved control. Okay, this is the hardware result for the 6-phase. Their reconstructed current, one phase inductor current as well as their reconstructed current, they are almost the same, almost same. So what is time now? So these are the few currents. Now I would like to know, if you have a doubt till this point, you can, it is open to ask. You can ask anyone. Anyone from our side, if they wish to ask, please feel free to ask in between. Any question?
Sir, in case if there would be any question, I think we will take care in the last.
Okay.
What type of microcontroller that has been adapted, sir?
I have shown you the STM32F. I have just let me show that it is STM. Somewhere I have given this figure. I think. Yeah, this is the discovery board which we are using, STM32F407VG. This is the controller board which we are using. All the sensors, voltage sensor output, they are going to ADC. and timers are reconfigured to generate the pulses for the gate drive circuit.
Is it inbuilt, sir? It is being developed by.
No, it is here. Please see, it is a, since we are working in the laboratory, they
Yeah.
are purchased, and you can use the individual. It's coming around 5,000. It's nearly about 5,000, and you can train. But because of some protection and some ADC facilities, you need to scaling the voltage signals. Then some features are they are adding, and they are costing to around 20 to 25,000.
That complete controller, sir. SM.
Yes, STM32 407 controller board, along with the all the accessories like supply, then scaling, you can get it 20 to 25,000.
What
But
is
if
the
you
specifications of the switches, sir? V by dV by dt and di by dt rating.
this switches, IGBT switches we are using in the laboratory purpose, they are designed with details. It's around 1200 volts we are using,
Oh,
and the 1200 is the 70 ampere, and 1200 volt is the IGBT module, and 20 kilohertz is the operating frequency. Okay.
okay.
Maurya sir, I also have one query. For what purpose this single phase variac is used?
This you are talking about R load?
No. Single phase variac.
Okay.
It looks like auto transformer. It is.
Yeah.
Then
The
for
reason
what
is
purpose it is? Because the motor is three phase.
no. See here, see sir, there is a topology which I would like to tell here. This VSC, and there is a induction motor. The star point of this is connected to AC supply. Okay, and this midpoint is connected to AC supply. So this AC supply followed by the auto transformer single phase variac
Okay,
is
means
used to.
from single phase you are in between try to make this DC something like that.
Yeah.
Actually, my question is, I mean, how we practically realize this single phase transformer on the EV itself. That is my particular
No.
question.
I said na, whenever you need to charge your vehicle, you have
Then
to take
only,
power from the grid.
then
So,
only this is being
so you
used.
have to plug in your socket to the grid. There you can get 230 volt.
Okay, fine, absolutely
But in
fine.
the laboratory, we are reducing that voltage to lower voltage through the auto transformer, and then we are converting through diode bridge rectifier as a DC, and then VSC is used to make the PFC operation. I hope you got answer, sir.
Yes, sir.
Yes.
So could you please share the paper, sir?
Yes, it is available. You can scroll and you can get it. You just name the Google Scholar. Many papers are available here. Okay. So, any other doubt, if anybody has, I'm happy to answer. Otherwise, it look monotonous and it will be only one
Yes,
direction. I
I can
expect
understand.
you, everybody should participate so that we can, I also enrich from your knowledge. Okay.
Exactly.
So if anybody have any other query, yes, please. See, we have a very good support of industry also. Suppose if anyone wants to develop its prototype model in the laboratory, they can approach. We can provide with no time whatever support required. Okay. Only thing, you have to drop the mail. You have to have a fund at your end so that we can provide support to for that. So now that today we don't have only thing, you should have a will to do the things in your laboratory. Okay. So being a teacher, you should encourage your student to make the small project even during the coursework also. Like suppose if you are doing power electronic course in your lab in your college, you ask your student to design a driver circuit. You ask your friend to design a snubber circuit, and that model can be developed without no much investment. So only thing, you have to take initiative, you have to motivate your student to be in the lab, and they work with you in the lab. Okay. So, and that is why the student will be motivated to towards your teaching. Otherwise, if you do the conventional teaching without doing any novelty, any innovation in your teaching process, probably student will lose the interest and they will never turn up to your class. So what I suggest, always experiment new things in the lecturing, and encourage student to participate in the lab, not during the lab hours, even beyond the lab and lecture hours also. Okay. So and that we are trying to do at our place also. Okay. This is the one also integration we have done at our lab, our laboratory. In some of the research scholars, they did it, and here they are facilitating. Like, see, I have lower side figure. Here we have EV1 and EV2. So the two EV machine we have demonstrated, and we want to make the power transfer from one EV to other EV. Suppose one EV is full, is charged, other EV is discharged, and they are required to be charged. Then we can take the power from the EV, from this DC to DC converter. They can take power from battery to DC link, and this DC link is directly connected to the next vehicle, other vehicle, and this EV is able to take power and charge the vehicle. So the two vehicle can be charged, and the operation can be made as a V to V charging. So as I discussed, grid to battery charging, that is vehicle to grid to vehicle, is already there. I have already discussed. But vehicle to vehicle charging can also be done. It can be made. So if you see the Indian scenario, I think none of the vehicle have a multifunctional charge. Today, we have a facility where we are replacing the IC engine based vehicle. I don't think in India, suppose the e-rickshaw is very common in India, rural cities also, rural villages, some places. I have seen plenty of e-rickshaw are there, but are they facilitated? Are they featured with vehicle to grid? Are featured with vehicle to vehicle? Probably answer is no. Because in vehicle to vehicle, this feature is not available. So can we enrich this feature to our vehicles so that their operation, their optimum? This four vehicle model I have already said. So same thing is rearranged, and we have tried to maintain the things. If you see the control of entire, whether it is a vehicle to grid, grid to vehicle, or vehicle to vehicle, in all case, the front side, if you see this converter, so the presentation, no, not that. If you see this particular circuit, probably everybody know it. This is a simple PFC. Here we are generating reference current. Yes or no? DC link followed by the reference voltage followed by the DC link passed through the PI controller, and here we can use the voltage sense template of phase A, phase B, phase C, multiplying to get the each phase current. So this control is called boost PFC converter, and then it is compare with the individual motor winding current, and then it is passed through the PI controller to generate the reference current. So the all the six leg, all the six leg, they can be powered through a simple three-phase BFT PWM rectifier. It's a very common control, and one can ask questions here also. Here we have customized because each phase, their midpoint we have taken out. Each phase, their midpoint we have taken out. The purposely it is done so that when you are operating with three-phase supply, the rotating torque should not produce. Otherwise, while charging, you have to lift your vehicle from the ground so that it should not run. So you need to take change in this motor vehicle. But when you are operating with a single there is no question of rotating torque produced by the winding. So there is no provision you have to incorporate there. So that is why you have seen in some of the places I have used single phase supply in induction motor through the start motor, so that the no rotating torque is produced and machine is not operation during hours. So we need to take care. And again, when you are charging, when the battery is about to be charged, then obviously during CCC, you have to take charging or constant current charging. So any one of you have to select through the proper mode selection, and then it is going to charge your battery. Common techniques they are available, and they can be used to charge your battery. Okay, some of the test results we have taken, and they also comply. They also validate what we are expecting through the simulation. We are having simulation, and then we have tried to show the corresponding results in that. So these are the some test results, voltage as well as their current waveforms we have shown. Here during the simulation also, here the current is out of phase. You can see the power flow is reversed. Okay. These are internal switches waveform, their pulses, and these are the few references which we have. So that's all. Anything to discuss, I am happy to answer.
Thank you, sir. If anyone want to ask any question, you may unmute yourself and ask questions.
Jagdish Kumar Sab, the feedback link has been already shared. Might be you joined late. For you, I am sharing once again. Don't be rush behind the feedback. Try to get the knowledge which we are trying to impart you. Feedback certificate is the byproduct.
One of the students, one of the faculty, they have asked. I think we are reducing the end pollution. I am not able to answer. Understand.
Sir, actually, when you ask now why we use EV, I think at that time in the beginning, 4 o'clock somewhere around 4,
Okay,
9,
okay.
10. Then he said.
They started.
Then he written.
Burden on the.
G.
So here my purpose is we are encouraging vehicle, EV vehicle, but if you see the current use, normally the urban, even in the urban city, the EV is a car is not popular. But suppose to reduce the urban pollution like Delhi, Mumbai, even Surat city, we have overuse. But if you are using electric vehicle, probably we can reduce the pollution at the urban city. But charge this vehicle, let's say 10,000 vehicle charge through the power through our grid. You are taking power from additional 10,000 vehicle to be charged. So that much power you are taking from the grid, and to generate that you required again you are creating pollution at your place where the electricity is generated. Let's say you have a thermal power plant and you are generating excess energy to charge the additional vehicle. So here in nutshell, you can say you are polluting some other place, and you are not polluting your urban city. But in total, if you see that sustainable development, this is not the good practice. If you are using your vehicle, so you should in totally you should make the pollution free. So if you take charging from your PV, probably you will not pollute either in either places to get your energy. Answer to that. Okay. Any other question? Any other question?
Yeah,
I hope,
Maurya, I have one query.
Guru Swami sir.
Yeah, Maurya, see, whenever we go for any of the four-wheeler or maybe the truck, can you able to hear me?
Yes, yes, sir. Yes, please.
Audible.
When you go for the design of the charger for the four-wheeler, maybe rated for the 150 kilowatt, then what is the best suitable powertrain can be used so that we can charge the battery of the truck or maybe the higher end car?
See, let's say you can take, as per our literature, let me talk about this Chevrolet Bolt. Their battery capacity is 60 kilowatt hours and the voltage is 350 volt. Their onboard charger is rated for 7.2 kilowatt. So if you are using through onboard charger, the maximum current which can allow to charge your battery pack is up to the 7.2 kilowatt. Agreed, sir? Yes or no? Because if you draw excess power from the battery, your charger will burn. But if you utilize this motor winding, it is designed for 150 kilowatt rating. Capacity of battery charging is also good. And here power electronics converter, which during motoring mode like VSC and IGBT, these all are designed to carry 150 kilowatt at least power during the all operating condition. So we can design charging, yeah, we can facilitate charging of your battery with the rating up to the rating of the motor winding, VSC, and they are all cabling. So as motor is as the power electronic component involved during the motor driving, they are carrying design for high rating current. You can charge your battery to that rating, provided your battery should have a recommended that limit, because every battery pack or battery cell, they are given with the data how much recommendation, how much rating you can charge that battery. So since integration is done with the high power components, you can allow to charge up to the rating of the motor, up to the rating of the battery. Rating 70 battery capacity, and if it is allowed to recommend for 2C, you can go for the 150 ampere hour. Are you getting?
Yeah, I'm following.
Yes. Yes.
Yeah, thank you for the
Any
clarifications.
other? So hello. Hello.
Astosh?
Yeah.
Yes, sir.
Thank you, Rakesh Maurya.
Thank you. Thank you, sir.
Respected sir, on the behalf of organizing team, I extend my heartfelt vote of thanks for the insightful session on the topic integration on board electric vehicle battery chargers with multifunctional features. Sir, your lecture provided a comprehensive understanding of modern onboard charger architecture and their involvement involving role in the electric vehicle. The way you explained the integration of charging functionality with TFC, bidirectional power flow, and the auxiliary feature highlighted the practical significance of multifunctional converters in next generation EVs. Your clear explanation of design consideration and control strategies and real world challenges has greatly enriched our technical knowledge. The session not only strengthened our conceptual foundation but also inspired us to explore innovative research directions in the EV, power electronics, and charging infrastructure. Immense value to this FTP. Thank you once again, sir, for such a meaningful and enlightened session. Thank you, sir.
Okay. Thank you, Maurya Saab. On behalf of my personal as well as the HRD cell coordinator, I am very thankful you join us and deliver such a wonderful talk. So thank you once again.
Thank you.
And dear participant, we will start at 5:40. So only 9 minutes left. So no need to leave the meeting. Yes, Maurya sir, कुछ आप कह
Thank
रहे
you.
थे.
Thank you.
Thank
I
you,
can
sir.
leave.
Sanjay, sir.
Thank you.
जी sir. Maurya sir, are you saying?
Yes, sir.
Maurya, sir.
So may I leave, sir?
Yes sir, sure sir. Second, जी.
I will
Sure.
talk later.
Yeah.
Definitely.
Okay, sir.
Namaste.
Thank you.
We will start at 5:40, so be in the seat. And feedback of
Thank
the
you, sir.
session has been already shared.
Okay.
And for second session, we will share feedback once again. And once again, it is advised to all, please attend all the session and also ask your friends to attend, because we are very much stick on 100% attendance, 100% participation. Even though I'll try my level best to get this criteria relaxed, but for sure it would not be going to blow the 75%. So make sure you must attain at least 80% or 90% of the session. Thank you very much.
Thank you, sir. Thank you.